Greetings and welcome to a new series on set theory. In light of the coronavirus, I'll be uploading some lecture materials for O-level studies and revision. So without further ado, let's begin. The success criteria for today's lesson is for students to be able to list the elements of a given set, apply the correct set notation in given relationships, and to be able to find the complement set, the intersection, and the union of two given sets A and B. So what is a set? A set is a well-defined collection of distinct objects. Distinct means that every object in the collection must be different. Well-defined means that if I give you an object, every reasonable human being can agree whether the object belongs or does not belong to the collection. Take, for example, prime numbers. Prime numbers are numbers with two distinct factors. We can all agree that 7 is a prime number. Or the K-pop group BTS. The members belonging to the group is not for debate. But if the description is something less clear, like the top 10 largest number, that is not well defined. I can't tell you what the largest number is. Or take, for example, the set of cute Pokemons. Cute is a vague term. Some people might consider this Snubbull cute, some might not. It's ambiguous. There are three ways to define a set. We could try to describe it in words. We use capital letters to represent the collection, and the description must be precise to avoid ambiguity. Without this word inclusive, someone reading this statement may not be sure if we want the number 2 or 12 to be inside this set or not. The second option is to list out all the elements. Elements is just another name for all the objects that make up the set. We use curly brackets to delimit the set. As I always say, practice safe sets. Use brackets. However, this approach can be potentially tedious or impossible when it comes down to infinitely large sets. Lastly, we can use set builder notation, which is succinct and clear. In this given example, set A is a group of elements X, such that X is equals to 2k, k lies between 1 and 6 inclusive, and k is a natural number. Let's pause here to check your understanding. Could you list out the elements for sets A, B, and C? Pause the video here to give this question a good try. Here are the answers. Set A contains 1, 2, 3, 6, 9, and 18. Don't forget to use the curly brackets to delimit your set. Set B are the multiples 3, 6, 9, 12, 15, and 18. And for set C, square numbers are all positive, so there are no negative square numbers. So we will have an empty set. Just put two curly brackets and leave it empty inside. Let us now run through some notations that we use for set theory, and we'll begin with symbols used to represent special sets of numbers. Let's start with natural numbers. These are the counting numbers like 1, 2, 3, 4, 5. This does not include 0. This symbol Z represents integers. Integers are all your natural numbers plus a little bit more. It includes 0 and all the negative counterparts of your natural numbers. The symbol Q represents the set of rational numbers. This adds to the set of integers by including any number that can be represented as a fraction of two integers p over q, whereby p and q are coprime and q cannot be 0. The letter R is a symbol used to represent real numbers. This would include all the other irrational numbers like pi, square root 2, and e, and this could be any number that is located along the number line. Next, let's look at symbols involving elements in a set. This E-like symbol means it's an element of. Like we can say that the number 2 is an element of the set containing 1, 2, and 3. Or we could say that Jin is a K-pop artist belonging to the group BTS. It's important that to the left of the symbol, it is always an element, and on the right of the symbol, it is always a set. If we cancel away the E, this symbol now means that it is not an element of. Like 4 is not an element of the group comprising 1, 2, and 3, or we can always say that Mr. Chen does not belong to the group BTS. This symbol of an N followed by an open and closed bracket refers to the cardinality of a set. This is basically just counting the number of elements within the set. For example, the set A comprising of the elements 0, 1, 2, and 3 has a cardinality of 4. So we say N bracket A close bracket equals to 4. Or for the example of BTS, there are 7 K-pop members, so the cardinality of that group is 7. This next symbol that looks like a U rotated 90 degrees clockwise means a proper subset of. For example, the set containing 1 and 2 is a proper subset of the set containing 1, 2, 3, and 4, because both elements in the smaller set, 1 and 2, can all be found in the larger set. It is very important that when you're using this symbol, both the left and right hand side of the symbol are both sets. On the other hand, if we cancel away the subset symbol, then the new symbol means not a proper subset of. In this example, the set containing 1 and 5 is not a proper subset of the set containing 1, 2, 3, and 4, because while 1 is found in both groups, 5, which is found in the smaller group, is not found in the larger group. To contrast between proper and improper subset, a set can never be a proper subset of itself. If we underline the proper subset of symbol, now the new symbol represents is an improper subset of. For the improper subsets, any set can be an improper subset of itself, like the set containing 1, 2, 3, and 4 is an improper subset of the set containing 1, 2, 3, and 4. This last symbol for subsets represents not an improper subset of. This is a less strict version of the previous not a proper subset of. Now let's check your understanding of these 4 symbols. Fill in the blanks with the 4 available symbols above. Pause the video here to give this question a good try. Let's now go through the answers. The set containing red is a proper subset of the set containing red, green, and blue. X is not an element of the set consisting of AX, BX, CX, and DX, because none of the individual elements in that set is exactly X. The set of prime numbers is not a proper subset of odd numbers because of the number 2. 2 is a prime number, but 2 is not odd. You only need one counterexample to disprove the subset property. Lastly, if we solve the equation x squared equals to 9, we get 2 solutions, 3 and negative 3. Therefore, negative 3 is an element of the set. Let's now look at some notations that denote special types of sets. The first type is the universal set. The universal set is a set that contains all possible elements. In this example, we can set the universal set to be the numbers from 1 to 10 inclusive. Subsequently, when we say that the set A are even numbers, A would only be the elements 2, 4, 6, 8, and 10. There will be no other elements because any other even number would lie outside the universe. The next notation looks like a 0 that has been cancelled. This is the null set, an empty set, a set which contains no elements, not even 0. The null set is a subset of all sets. The last three notations for today will be the operators of sets. The apostrophe sign, when it's placed after the set A, this represents the complement set of A. This refers to the elements that are not found inside set A. So if I have a universe containing 1, 2, 3, 4, and 5, and I say that set A contains 2 and 3, then the complement set of A would be the other three elements, 1, 4, and 5. The second operator is the intersection. When the set of elements in the set A is intersected with the set of elements in set B, we will get the set of elements that are common to both set A and B. For example, if set A contains 1, 2, and 3, and set B contains 2, 3, and 4, then A intersect B will be just 2 and 3. The last operator is the union. When we take set A union set B, we get the set of elements that belong to either set A, set B, or both sets. So in the example, if set A contains 1, 2, and 3, and set B contains 2, 3, and 4, then A union B would be 1, 2, 3, and 4. Let's end off with two worked examples. Here is example 1. Pause the video here and give this question a good try. Let's start with part A. So a good practice is to list out all the elements in the universal set first. So here we get the numbers 0, 1, 2, 3 all the way to 9. Out of all the elements in the universal set, the only even numbers are 0, 2, 4, 6, and 8. The prime numbers are just 2, 3, 5, and 7. Note that 1 is not a prime number because prime numbers must have exactly two distinct factors. From the answer in part A, we can now compare set A with the universal set to sieve out the complement set of A. So the elements not in set A are all the odd numbers, 1, 3, 5, 7, and 9. And we can do this for the complement set of B, and this will give us 0, 1, 4, 6, 8, and 9. In part C, we look at the elements in set A and set B, and we combine both set A and set B together to form the union, which would consist of the elements 0, 2, 3, 4, 5, 6, 7, and 8. Counting all these elements, this tells us the cardinality of A union B is 8. Lastly, we can use our answer in part B and compare those two complement sets. Here we can see that the only things they have in common would be the elements 1 and 9. So the cardinality of A prime intersect B prime is 2. And here we have example 2. Pause the video here and give this question a good try. Here is the answer for part A. This should be straightforward enough. For the first part of part B, we don't need to list out all the elements in the complement set of B, because the number of elements in B and B prime should add up to the number of elements in the entire universal set. Hence, we can subtract the cardinality of set B from the universal set, and this will tell us that the cardinality of the complement set of B should be 14. If we combine sets A and C together, A union C would be as follows. A tip would be to try to arrange it in ascending order to prevent double entries. Counting the elements tells us that the cardinality of A union C is 11. Now, to find the cardinality of A intersect B, we need to see what these two sets have in common. It turns out that this is impossible. It's impossible for an odd number to also be a multiple of 4. So A intersect B is a null set. Hence, the cardinality of A intersect B is 0. For this last part, we need to first find all the elements that are not in B and that are not in C and compare these two complement sets together. Counting the common elements, we arrive at the cardinality of B prime intersect C prime to be 12. Now it's time for you to do more practice on your own. Some additional practice can be found in the info section. I've attached a link to a worksheet for extra practice as well as a solution sheet for you to self-check all your answers once you are done with the worksheet. Before we end, let's go back to the beginning. Let's reflect on the success criteria that we set out at the start of the lesson. Are you now able to list out the elements of a given set, apply the correct set notations for given relationships, and find the complement set, the intersection, and the union for two given sets? Comment in the comment section below if there are anything that you might find unclear or unsure about. We have come to the end of part 1 on set notation. Stay tuned to part 2 of set theory where we will cover Venn diagrams. Thank you and have a good day of learning.